in continuous time, we can also define the unit step function as something similar. Right? It's basically a signal that is equal to 1 for t greater than 0 and 0 for t less than 0. Okay? So if you plot this out, the unit step function u of t looks something like this. Right? You have the value 1 on the positive axis and the value 0 on the negative axis. Okay. So you see here that we're not specifying what is the value at time 0. Okay? So you can see here that there is a discontinuity at time 0, but we're not specifying exactly what this value is. Right? Now, in some textbooks, right, in some contexts, you will see people defining this, associating the time 0 with value 1. Some people associate it with value 0, and some people associate it with value 1/2. Okay? But this will not be, essential for us at this point, so we're going to leave it undefined right now. Okay? It doesn't really matter for us at this point. Okay? But basically, what matters is that this unit step gives you 1 in a positive axis, 0 in a negative axis, and there's a discontinuity here. Okay. And then, with this unit step function, we can then define a unit impulse function, delta of t, as a function that integrates into this unit step function. Okay? So we define the unit impulse function, delta of t, as a function defined such that its integral up to time t gives you the unit step function. Okay? Now, if u of t is the integral of delta of t, then we can sort of view the unit impulse delta of t as the derivative of this unit step function. Okay? We can sort of do this, but there is some difficulty because in reality, this unit step function is not differentiable at time 0. Right? There's a discontinuity here. Right? So a discontinuity is not differentiable. Okay? So if you're a mathematician, right? Mathematicians are typically not very happy with our use of these unit step and unit impulse functions, but they are very useful for us from an engineering perspective. Okay. But if you want to be more mathematically rigorous, right, one way to look at this unit step and unit delta, unit impulse functions, okay, is treating them as idealizations of functions like this. Okay? Now, if you look at this unit step function, right, this is a function or a signal that rises abruptly from 0 up to 1. Okay? Now, in practice, no signal can actually rise abruptly from one value to the other. Okay? In practice, you must always have some non-zero rise time in order to go from one value to the other. Okay? Now, the unit step function you can view as an idealization of a function like this, where delta is infinitely small. Okay? And why is that reasonable? This is reasonable because in practical systems, even though the signal may not rise abruptly, but as long as the response of our system is much slower than the rise time of this signal, then to the system that we're looking at, there's no significant difference between this signal and this signal. Okay? So if you pass a signal like this through a system, that responds much slower than the rise time of the signal, then to the system we're looking at, there's no significant difference between this signal and this signal. Okay? So even though in practice no signal really rises abruptly, but mathematically this brings us some convenience. So we deal with these signals most of the time. Okay? And as long as this rise is fast enough, it should not be much of a problem, between theory and practice. All right? But basically, this is an idealization of a practical signal like this. Okay. So more specifically, here we're defining a more practical signal as this u sub delta of t, this capital delta of t, which represents the rise time, right? The time it takes to go from 0 up to 1. Okay. Now, given this, practical unit step function, if we take the derivative of this, we will then get a practical, impulse function like this. Okay? So this delta sub capital delta of t can be viewed as the derivative of this practical unit step function u sub capital delta of t. Okay? So you can check if this is true, right? So at this point, the derivative is 0, but at this point, the slope is 1 over delta, right? So within this interval, the derivative is 1 over delta. And then once you reach this point, the derivative becomes 0 again. Okay? Right. So this is just something you might want to be aware of. Right? So even though, we might, throughout the course, we might use this kind of interpretation for the delta function. But, in your mind, you should know that this is, not formally differentiable. Okay? So you should keep in mind that this delta function should be viewed as an idealization of a very short pulse okay, an idealization of a very short pulse like this. Okay. All right. So if you view u of t as an idealization of this u sub delta of t as delta goes to 0, then you can view this delta of t as this delta sub capital delta of t as capital delta goes to 0. All right? Okay. So this is what I just mentioned. Right? A unit impulse can be viewed as the limit of this very short pulse as the pulse duration goes to 0. Okay? So this thing is a very short pulse. Then we let the pulse duration go to 0. Okay? Now, as delta becomes smaller and smaller, 1 over delta becomes larger and larger. Okay? So as delta goes to 0, the area of this pulse does not change. It's always unit area. So the magnitude right, the height of this pulse must gradually go to infinity. Okay? So when we draw this unit step function, we're accustomed to drawing this, drawing an arrow going upwards, indicating that the height is infinite. Okay? But we still draw the arrow with the length that represents the area of that pulse. Okay? So we label, right, or draw the arrow with the length 1 that represents the area of the pulse. Okay? So if you view delta of t as a limit of delta sub delta of t, right, as delta goes to 0, this pulse is essentially has no duration. Okay, but still maintains the unit energy, unit area, and therefore has, infinite height. Okay, and in practice, you can view this as an idealization of a very short pulse. Okay. All right. Now, if you look at a scaled impulse, right, if you scale an impulse function by the scalar k, then what you're saying is that now you're looking at a very short pulse with area k. Okay? And consequently, right, if you integrate this k times the delta function, okay, then since the integration of the delta function becomes the unit step function, sorry, I think I should have a tau here instead of t. Okay. So consequently, if you integrate this k times the delta function, what you get will be k times the unit step function. Okay? All right. So since a scaled version, right, since a delta function scaled by k gives you a very short pulse with area k, therefore, when we plot this scaled impulse on a graph, we will scale the length of this arrow accordingly. Okay? So this k here represents, both the area or the scale that we're imposing on a delta function. Okay. All right. So as we just mentioned here, right, suppose you look at the case where k equal to 1, then we know that u of t can be written as the integral of delta of tau d tau. Okay? And this can be interpreted similar to the running sum that we had in the discrete time case. Okay? So this is because what we have here is actually the integration over the delta function. Okay? So the delta function is a function here, okay? And what we're integrating is this delta function from minus infinity up to time t, okay? Right? So you can interpret this unit step function as a running sum of this delta function from minus infinity up to time t, right? So this is consistent with our interpretation in the discrete time case, right? Something like this. Okay. Now we can also do a change of variable suppose we do a change of variable where we set sigma equal to t minus tau. Okay? So in this case, right, we're integrating over delta t minus sigma minus d sigma. Okay? So we're replacing tau with t minus sigma. So d tau with minus d sigma, okay? Then the integral originally from minus infinity to t now goes from infinity up to 0. Okay? Now, if you flip this around, right, if you flip this around, we get a negative sign that cancels out with this. So if you flip this around, you will get an integral from 0 to infinity delta t minus sigma d sigma. Okay. So this is another way to represent the unit step function in terms of the unit impulse function. Okay. And what does this mean intuitively? Right. So in this case, what you're integrating is this delta function here. Okay? Right. And now the time variable is sigma. Okay? So delta of t minus sigma is basically a delta function shifted to time t. Okay? So this is basically a delta function shifted to time t. So suppose that this t is somewhere here. All right, so this is delta of t minus sigma. Okay? And we're integrating this delta function from 0 to infinity. So the range of integration is from here up to infinity. Okay. So if t is negative, then we're integrating over nothing, right? So if t is negative, then we're integrating over nothing, so u of t is 0. Now, if t is positive, right, if the delta function is somewhere here, then we're integrating over a delta function which has area 1. So if t is positive, then u of t will be equal to 1. Okay? So these are two different ways of, looking at the unit step function in terms of the unit impulse function. Okay? All right. Now we mentioned that the unit impulse function is, useful for us to represent a sampling operation, right? Similar to this example here for the discrete time case. Okay. Now you can do something similar in the continuous time case. Right. Now in the continuous time case, right, suppose that this is the signal we're looking at, right? This is x of t, and we want to sample it at, let's say, time 0, okay? So, right, now suppose that we start from the original practical short pulse, delta sub capital delta of t, okay? So when you multiply this x of t with this short pulse, delta sub capital delta of t, what you get is a function that is 0 everywhere, but a part of the signal x of t within this duration and 0 everywhere else. Okay? So when you multiply the two, right, basically taking x of t times delta sub capital delta of t, you get a function like this. All right. Now, when delta is very small, you can approximate this function with a function where we have a square here multiplied by the value of x at time 0. Okay? So we can approximate this red curve here with this x0 times delta sub capital delta of t, which is basically this function here. Okay? So you can see that there's only a very small discrepancy between the two functions. And this discrepancy vanishes as capital delta goes to 0. Okay? Therefore, as delta goes to 0, my left-hand side becomes x of t, delta of t, and my right-hand side becomes x of 0, delta of t. Okay? So this is analogous to the sampling operation that we had here. Okay. So here in the discrete time case, when we sample the function by multiplying it with the delta function at time n naught, we will get the value of the function at this point times the delta function. Okay? Now, in the example we just showed for continuous time, we're just looking at the case where n naught is equal to 0. But this actually holds, right, in general. Right? So similarly, if you sample the function at time, let's say t naught, then similar to before, this will extract the value of x at that time times the delta function. Okay? And these are representations of the sampling property. Okay? Right. So this remark I already repeated several times, but I think it's an important concept to understand. Right? So when we talk about these unit step functions or unit impulse functions, right? Even though in practice, you would not really see a signal that rises abruptly as a unit step function, or you would not see a very short pulse with 0 duration and infinite height, right? This is not possible in practice. But these functions, right, are convenient for us mathematically, and they are idealizations of these very short pulses that we just talked about, right, that would not make a significant difference if your system response time is much slower than the actual rise time of these signals. Okay, so if your actual rise time of these signals is much smaller than the response time of your system, then considering these ideal pulses would not make a big difference in your study. Okay? Okay. Now let's look at a simple example of using these step and impulse functions. Okay. So here we're looking at a function x of t that looks something like this, and we're asked to find the derivative of x of t. Okay. Now, when you look at x of t, you can see that it seems like a combination of these rectangular-shaped signals. Okay. So, and indeed, we can write this x of t, okay, as a linear combination of time-shifted unit step functions. Okay. So first of all, when you go from the negative axis up to time 1, right, you see an abrupt rise from 0 up to 2 at time 1. So this abrupt rise you can represent as a unit step function at time 1. Right? So this is 2 times u of t minus 1. Okay? So at time 1, I have a rise of 2, right? I have rise up to 2, okay? And then I will remain 2 the remainder of the time if there are no other functions existing, okay? But then we see that at time 2, we jump down to minus 1, okay? So the way to go from 2 to minus 1 abruptly is by adding another unit step function at time 2 that has a magnitude of minus 3, okay? Has an amplitude of minus 3. So if we subtract a minus 3 u of t minus 2, okay, this will allow our function to go from 2 to minus 1 at time 2. Okay. Now, if we do nothing else, this signal will remain here for the remainder of time. But we see that it rises back to 1 again, right? Basically rises by 2 at time 4. Okay? And this is done by adding 2 times the step function at time 4. Okay? So this signal x of t here can be written as a linear combination of these time-shifted unit step functions. Okay. So then if you're asked to find the derivative of x of t, we can then express the derivative of x of t as a linear combination of the derivative of these unit step functions, which we define as the unit impulse. Okay? So therefore, the derivative of x of t we can write as 2 times delta of t minus 1 minus 3 times delta of t minus 2 plus 2 times delta of t minus 4. Okay? Now, if you plot this out, So if you plot this out, we will have a unit impulse function, a delta function at time 1 scaled by 2, okay? So I should have a delta function at time 1 scaled by 2, meaning that the arrow must have a length of 2. Right, so I should have this arrow here, okay? Then at time 2, I have a delta function scaled by -3. So the length of the arrow now must be 3. But because of this negative sign, I now draw the arrow in the negative direction. Okay? And then the last term gives you another impulse at time 4 and also with area 2. All right? So this is the derivative of a signal like this, right? Written in terms of a combination of unit impulse functions. All right, so these, this part and the parts that we covered in previous classes introduces you several basic signals that we will use, throughout the lecture, okay, throughout the course. Now, covering some basic signals, what comes next is naturally, what are systems, okay?